Hello, everyone, and welcome to today's science lesson radioactivity. Have you ever wondered why some elements are stable while others decay and release energy? In this lesson, we will explore what makes atoms radioactive, how they change, and how scientists study and measure these transformations. By the end of this lesson, you will understand difference between natural and artificial radioactivity, the laws that govern nuclear reactions, the main types of radiation, alpha, beta, and gamma, and how we calculate radioactive decay, energy, and activity. So let's begin by the atom. Certain atomic nuclei are unstable. They contain too much energy or unbalanced ration of protons and neutrons. To become more stable, these nuclei transform into other elements by emitting radiations. This transformation is what we call radioactivity. There are two types of radioactivity: natural radioactivity, which happens spontaneously, like in uranium or radium; artificial radioactivity, which is induced by humans when scientists bombard stable nuclei with particles to make them unstable. Conversations laws. When a nucleus changes, it follows very strict conversion laws, known as Soddy laws. Let's consider original nuclear reaction. X with AZ can give Y with A1Z1 and P with A2 and Z2. Here, X is the parent nucleus, Y is the daughter's nucleus, and P is the emitted particle. We have two rules always apply. Conservation of nucleons, the total mass number stays the same, A equal I1 plus I2. And the second is conservation of charge. The total number of protons remains constant, Z equals Z1 plus Z2. This means during any nuclear transformations, no nucleons or electric charge are lost. They are just rearranged. Next, we will talk about natural radioactivity. Natural radioactivity is a spontaneous process where unstable nuclei release energy by emitting radiation. There are three main types: alpha, beta, and gamma radiation. We begin by alpha decay. Alpha decay happens in very heavy elements, those with atomic numbers greater than 84, such as uranium or thorium. These nuclei have too many protons and neutrons, which making them unstable. To become stable, they emit an alpha particle, which is a helium nucleus, He, A4, and Z2. The original equation is X with A and Z can give Y and emitting alpha particle. For example, uranium can emit alpha particles and product thorium. This emission decreases the atomic number by 2 and the mass number by 4, producing a new element. Beta minus decay. Next is beta minus decay, which occurs in neutron-ish nuclei, where there are too many protons compared to protons. In this process, a neutron transforms into proton, and electron is emitted. The equation is this increasing the atomic number by one, turning one element into another, but the mass number stays the same. For example, carbon can form nitrogen with emitting beta minus particles. This is how carbon 14 decays naturally into nitrogen 14. This process used in carbon dating. After alpha and beta decay, the new nucleus is often left in an excited state. To release this excess energy, it emits gamma radiation, which is not a particle but a high energy photon or magnetic radiation, and can be explained by this equation. Unstable barium can transform to stable barium with emitting gamma radiation. Gamma rays are the most penetrating from radiation, capable of passing through thick layers of materials. There is also beta plus decay or positron emission, which occurs in proton-rich nuclei. A proton converts into a neutron, releasing a positron and a neutrino. Following this equation, this process decreases the atomic number by one, helping the nucleus reach balance. Now let's talk about artificial radioactivity. When stable elements become radioactivity through induced nuclear reactions, scientists bombard stable nuclei with particles like neutrons or protons to create new isotopes. This process is used in medical imaging, cancer treatment, energy production in nuclear reactors, and even in scientific research. They have also many types of nuclear reaction transmutations, fission, fusion, plus emissions. Energetic aspect. Every nuclear reaction releases energy due to a tiny loss of mass, delta M. Einstein showed that this lost mass converted into energy by these equations. Let's take an example. Thorium can be transformed to radium with emitting alpha particles. And we have the mass of thorium, the mass of radium, and the mass of particle of helium. Delta M, which will equal 4.78 megaelectron. This energy corresponds to the kinetic energy of emitted particles and radiations. Radioactivity decay is a statistical process. The rate of decay is proportional to the number of stable nuclei present. The law is expressed as minus dn per dt equal lambda n. After integration, we get these equations: n equal n0 exponential minus lambda t, where n0 is the initial number of nuclei, n is the number of time, and y is the decay constant. Half-life t. The half-life is the time required for half of a radioactivity sample to decay. The decay laws. Each isotope has its own characteristic half-life, from fraction of second to billion of years. For instance, carbon-14 has a half-life about 5,713 years. Activity A. The activity A of a sample measures how many decays occurs per second, and given by relation A equals lambda n, and it's expressed in becquerel or Curie. Activity also follows the same decay law. A equal I0 exponential minus lambda t. Mass relationships. Since the number of nuclei related to mass, we can write n equal m times n per m. This which give the new relations m equal m0 exponential minus lambda t. This tells us the remaining mass of radioactive special decreases exponentially over time. Thank you for watching and don't forget to like, share and subscribe for more science lessons.